Welcome back to another video about the Haswing Protruar 2.0 24V trolling motor. During the unboxing and first impression video, it turned out that the 3 LED battery indicator of that thing is basically unusable. A card here and links to all other Haswing videos in the description. In this video, we will reverse engineer that thing and see if we can improve it. Enjoy! So, what was the problem with that thing? We have 3 LEDs here, and according to the manual, the first green LED, that one, indicates a charge state of 100%, the second green LED a charge state of 50%, and then the third LED, which is the red one, a charge state of 20%. A more sensible interpretation, and remember that manual was translated from Chinese, would be if the first green LED goes off, our charge state is at 50% or below. If the second green LED goes off, our charge state is at 20% or below, and the red LED is basically always on. Now, that would also be okay, but for the fact that the first green LED goes off below 23.2 volts, the second green LED goes off below 22.2 volts, and the red LED goes off, somewhere below 70.1 volts. But a lithium iron phosphate battery reaches its 10% charge state at about 24 volts, meaning all LEDs would be on all the time from 100% charge state to 10% charge state. And at some point, of course, all LEDs go off because the battery protection circuit will disconnect your battery. It's no better for AGM batteries if you are a lead acid fan. So they reach their 10% charge state at 23.0 volts. So at least when we are approaching 10%, the first LED would go off. So let's reverse engineer that bugger then, shall we? I mean, there's not too much to it, is there? So I took a photo from the front and one from the back. The problem is everything is thickly coated in conformal coating, which is a good thing because it makes it water resistant, but it makes probing the circuit a pain in the behind. So this will probably take the better half of the evening. I'll get back to you when I'm done. Okay, I'm finished. Here's the circuit diagram. 2 remarks. First, I know it's ugly. We have a lot of wiggly lines and lines crossing. But that's because I tried to retain the relative positions and orientations of the parts on the PCB. And second, of course, it might contain mistakes. But that circuit here should work. Battery minus comes in here and that's our common ground. Battery plus comes in here and goes through a part marked 1M. That's probably a polyfuse or something. Then the input is filtered by a 4.7 microfarad electrolytic and a ceramic. That TL431 shunt voltage reference and that 3.6K resistor create a 2.5 volt reference voltage rail. And the voltage divider here goes, of course, from the battery voltage to the ground. Then we have our 3 LEDs here, red, green and green, each with a 10K resistor going to the battery rail in series. So you have to pull these ends low to light them up. On this side we basically have 1, 2, 3 voltage dividers, which are a bit buffered with 3 ceramic capacitors. Going to ground, we always have 4.3K resistors. And here, going to the battery rail again, we have 2 resistors in series for each. They fiddle together 2 resistors in series, always a smaller one and a larger one, so they could get 3-digit resistor values. For example, this here has a 34.5K. Now, the outputs of these voltage dividers go into our mystery chip, which is a quad comparator. Something like a LM2901. I can't be sure, I can't read the markings. Anyway, they all go into the negative inputs, while our reference voltage goes always into the positive inputs. So, if an output of a voltage divider reaches our reference voltage, the related output will be pulled low and the related LED will light up. That's it. Now, the first voltage divider for the first green LED reaches 2.5 volt at the output when the input is 22.6 volts. The second one for the second green LED at 21.5 volts, and the third one for the red LED at 16.5 volts. If we have a look at the switching voltages according to the circuit for the 2 green and the red LED, and what I measured in that aforementioned unboxing and first impression video, we see there are some discrepancies. So the error for the first green LED is plus 0.6 volt, for the second 0.7 volts, and for the red 0.6 volts. In percent, that's plus 2.7%, plus 4.7%, and plus 3.6%. Now, an error of 0.6 volts when measuring a lithium iron phosphate battery can be, worst case, the difference between 70% charged and 30% charged. So, yeah, that's also a no-go. But please note, my measurements and my calculations are through rounding errors, probably also plus minus half a digit off. Now, where are these large errors coming from? There are basically 3 possible sources. First of all, our voltage reference. There are cheaper TL431 variants out there with a tolerance of plus minus 2 volts. Also, maybe they used here resistors with tolerances for up to 5%. And finally, that can be a really cheap LM2901 compatible comparator with really high offset voltages. To find out what is what, we have actually to measure that thing here. To do that, I will have to remove the conformal coating, at least for the relevant parts, and I will be using acetone for that purpose. So I set my lab power supply, which is feeding the whole thing, to 22.6 volts, and we will measure at the right pin of our comparator, nominal 2.5 volts. Let's see. 22.599, close enough. Two LEDs are on. And I want to measure here pin 10, input 4. And we only have 2.433 volts. That's not promising. I'm now down at 21.5 volts and only the red LED is on, which should be off, but I'm measuring now the voltage divider for the second green LED. That should be pin 8, and we got 2.42 volts. Yeah, that's really bad. Really bad. Finally, a 16.5 volts for the red LED comparator. That's pin 6. And we're here at 2.409 volts. Okay, the only thing missing now is the reference voltage, which should be available on pin 7. Let's see. Oh, the reference voltage is nice, 2.498. I mean, nothing to complain about. So, yeah, the resistors are really have high tolerances. Let's put it like that. Another advantage of removing the conformal coating is I can now read the chip's markings. And the comparator seems to be an original Texas Instruments LM339. And our voltage reference is, can you read that? Sorry for the shaking hand, TL431A. Anyways, we set the input voltage to the nominal voltages at which the two green LEDs, respectively the red LED, should switch on. So the nominal output after the voltage dividers should be 2.5 volts in each case. That's what we measured in reality. That's the absolute error between 0.07 volts and 0.09 volts. And this is the error in percent. So, yeah, the voltage dividers are clearly the culprits. And these numbers here are not directly comparable with those numbers because, we measured here the input voltages from nominal to measured. And here we have nominal to measured at the 2.5 volt range and the other way around. You could, in theory, do the math here, but for us it's enough to know that the voltage dividers are the problem. So, how can we improve that little circuit here besides using resistors with lower tolerances? Well, first of all, I want to use all 4 display states. I mean, we only have 3 LEDs, but that gives us 4 states. All LEDs on, a green and a red one, only a red one, and all off. I know, the latter here will be controversial. But hear me out. These 3 LEDs will all be switched off when the battery protection circuit is cutting the power. And wouldn't it be a good idea if they all go off before that happens? Anyway, we could use a linear voltage scale. So the red one lighting up at 24 volts, the first green at 25 volts, and the second green at 26 volts. However, for lithium iron phosphate batteries, That would translate to a charge state of 40% to 100%, then approximately 15% to 40%, and 10% to approximately 15%. And if all LEDs are out, we're at a charge state below 10%. The reason being that the charge state of a lithium iron phosphate battery is not linear with its voltage. You first have a steeper drop, then you come here into a kind of a plateau before the voltage goes down again, steeply again. And that plateau where you have, only very small voltage changes is from 60% to aboutish 40%. There you only have voltage changes between 0.0 volts and 0.1 volts. That also makes implementing a linear charge scale in 25% steps quite complicated, because here in the middle the green LED should light up at 26.1 volts, but that could also be 60% and is only 0.1 volts apart from 40% charge. So yeah, that's probably not working with that simple circuit here. Also, a non-linear scale would be hard to implement. For example, here I have the top 40% of charge, then the middle 30% of charge, then the lower 20% of charge, and then rock bottom 10% of charge. Here again, we have switching voltages of 24 volts, 25.8 volts, both would be okay. But then we have again those 26.1 volts, which could be 50% or 60% and only 0.1 volts away from 40%. So, yeah. So I decided I will use 30%, 30%, 30%, and then the bottom 10% scale. I mean, you really don't want to discharge your battery below 10%, life cycle and such. And here we get quite reasonable switching voltages of 24 volts, 26 volts, and 26.4 volts. Also, this roughly relates to the old rule. Yeah, you use a third of the tank to get there, another third of the tank to get back, and you have a third of the tank in reserve, and you never empty your diesel tank. Perfect. Let me know in the comments what you think about my idea for the scale. That's it for today. In the next video, which should be carded somewhere here as soon as it's published, we will actually do the work and exchange these 8 resistors there. And I will implement, of course, my scale, but I will provide the math so you can modify your battery indicator to your requirements. I'm talking about you AGM lead acid guys. Till then, bye.